Welcome to Physics for All YouTube channel. In this session, I am going to explain you about theory of Newton's rings. This question can be asked in the examination. Either a direct question is theory of Newton's rings, and indirectly they may ask derive conditions for the diameter of bright ring and dark ring using Newton's rings experiment. In order to get conditions for these Newton's rings, first of all, consider plano-convex lens and a plane glass plate. Arrange plano-convex lens and the plane glass plate as shown in this figure. Already we discussed about experimental arrangement of Newton's rings in the previous session. Today's class extension of the previous class. Now this is a plano-convex lens and it is the plane glass plate. Between the plano-convex lens and the plane glass plate, non-uniform air film present of thickness T. Due to the presence of non-uniform air film, at the center of the contact there is no gap. Because of this reason, constructive interference takes place, which results dark region at the center of the ring. Already we discussed in the previous session. Now in this class, our main concept is to derive conditions for the diameter of the bright ring and dark ring. So for this one, let us consider this geometry. So extend the plano-convex lens in the form of a spherical shape. Let us see is the center of the sphere. Then R is the radius of curvature of the plano-convex lens. L is the plano-convex lens and T is the thickness of the thin film which present between the lens and the glass plate, and small r is the radius of the rings formed due to the interference phenomena. Now here I am going to use property of the circle, that is horizontal line, that is NA into NB is equal to vertical line, that is NO into ND. So from this figure, NA is equal to NB is equal to radius of the ring and NO is equal to thickness of the thin film. Now substitute these values in the equation number 1, that is R into R, that is equal to T into 2R minus T. So how we are going to get 2R minus T? 2R minus T belongs to ND value. ND is the distance between here N to D. So C to D distance is radius of curvature and C to O distance is diameter, that is equal to 2R minus T, nothing but the value of ND. So therefore in equation number 1, in the place of NA, NB using small r, in the place of NO using small t, that is thickness of the thin film, air film, and ND is equal to 2R minus T. Multiply R into R square, that is equal to T into 2R 2RT minus T into T square. Now in this equation, that is R square is equal to 2RT minus T square. T is the thickness of the air film which is very small, therefore T square value still becomes very small, so we can neglect this T square value in the above equation. Therefore R square is equal to 2RT. Now T is equal to R square divided by 2R. Now our concept is to derive conditions for the bright ring. So this already we discussed in the previous class. So 2T is equal to 2N minus 1 into lambda by 2, where N is equal to 1, 2, 3 and so on. Now in this equation number 3, now substitute T is equal to R square by 2R. So that is 2 into, in the place of T, substituting R square by 2R, that is equal to 2N minus 1 into lambda by 2. So here this 2 and this T is going to cancel. Remaining part is R square is equal to 2N minus 1 into R lambda divided by 2. Now radius is equal to diameter by 2. Now substitute in the above equation, the place of R, small r is nothing but radius of the ring, that is equal to diameter by 2. So R square becomes D square divided by 4, that is equal to 2N minus 1 by 2 into lambda r. Now here 2 1s 2 2's cancel and d square is equal to 2 into 2n minus 1 into lambda r. We need equation for the diameter only. So diameter of the ring becomes d is equal to square root of 2n minus 1 into 2 lambda r. Now in this equation we are separating variables and constants. Here lambda is the wavelength of the light source used, which is a constant, and r is a radius of curvature of the lens. Already it is given by the respective supplier of the lens, and n is a variable. Therefore separating variables and constant, we are going to get d is equal to square root of 2n minus 1 into square root of lambda r. So d proportional to root of 2n minus 1, where n is equal to 1, 2, 3, 4 and so on. This is the condition for the diameter of the bright ring. Now substitute n is equal to 1, so we will get 2 into 1, 2n minus 1, so we will get odd number. And now substitute n is equal to 2 into 2, that is equal to 4, 4 minus 1 root 3, we will get odd number again. Now substitute n is equal to 3, 3 2s are 6, 6 minus 1 5. So in each and every step we are going to get odd natural number. So diameter of the bright ring directly proportional to the odd natural numbers. This is equation number 5. Similarly, we have to derive condition for the diameter of the dark ring. So already we derived in the last class, that is 2t is equal to n lambda, where n is equal to 0, 1, 2, 3 and so on. That is equation number 6. Now this equation number 6, again substitute t is equal to r square by 2r. Already we discussed in the previous case, t is equal to r square by 2r. This is equation number 2. Again substituting t is equal to r square by 2r. So 2 into r square by 2r, this is equal to n into lambda. Here this 2 is going to cancel and get the equation for the r square. R square is equal to n lambda r. Okay, now substitute r is equal to diameter by 2, therefore d square by 4 becomes n lambda r. Again we need equation for the d square only, so d square is equal to 4n lambda r, or this equation can be written as d is equal to 2 root of 2n lambda r. Now in this equation we are separating variables and constants again. D is equal to 2 into root of lambda r into root n. So lambda r is the wavelength of the light source and r is the radius of curvature of the lens. These two are the constants. This equation can be written as d proportional to root n, where n is equal to 0, 1, 2, 3 and so on. This equation can be written as d proportional to natural number, equation 5. This equation 7 and equation 5 are the conditions for the diameter of the bright and dark ring used in this concept. So this is about Newton's rings theoretical part. It is also called the discussion of diameter of bright and dark ring using the Newton's rings experiment. In the next session we are going to discuss about applications of Newton's rings. Generally this concept is important for the laboratory point of view. In rare cases this question can be asked in the university examinations also. Now the first application of Newton's rings is we can find wavelength of the given light source if you will know radius of curvature of the lens. And the second application is we can find refractive index of the unknown liquid. These are the two main applications of the Newton's rings. In order to find wavelength of the light source or refractive index of the given unknown liquid, first of all we have to arrange the given components like plano-convex lens, plane glass plate and travelling microscope, monochromatic light source, all components as shown in this diagram. Already we discussed this concept in the previous class. Now this is a diagram represents applications of Newton's rings. Now due to the interference between the reflected light rays from the upper part and lower part of the light rays, interference is going to form. Because of interference, rings are going to observe. These rings can be seen using the travelling microscope. Now we will go to the application point of view. Now using the travelling microscope we have to set the Newton's rings at the center of the crosswise for the traveling microscope. Now rotate the screw connected to the, this is a traveling microscope. This screw contains, this traveling microscope contains one screw. By rotating the screw either clockwise and anti-clockwise, the position of the microscope is going to change. As position of the microscope is going to change, arrange the microscope position from 0th ring to 5th ring, 10th ring, 15th ring, 20th ring and 25th ring. Like this, we can move the microscope position to the extreme left side, either any one ring. For example, I am keeping the microscope position at 25th ring. For this 25th ring, I am going to measure main scale reading as well as vernier scale reading. By adding MSR value and VSR value, I will get total reading for the 25th ring on the left hand side. Similarly, now rotate the traveling microscope screw in the reverse direction and come back to the 20th ring. At the 20th ring, again measure MSR value, VSR value and addition of MSR and VSR, which will give total reading. Like this, you can repeat the same procedure from the 25th ring to 0 ring on the left hand side and 0 ring to 25th ring on the right hand side. Again, all the values are tabulated in the table. Then by subtracting A difference B, we will get diameter of the ring. Then we have to square the diameter. What will get D square value. Now from the 0th ring to 25th ring, we can select any two rings. Then one ring is you can taken as M value, another ring is taken as N value. The respective value of D square, which will give Dn square and Dm square. Now using the formula, lambda is equal to Dn square minus Dm square divided by 4 into N minus M into R. By substituting the respective value from the table, Dn square value, Dm square value, nth ring number and mth ring number and radius of the curvature of the plano-convex lens, we can calculate wavelength of the given light source. This is experimental point of view. The same readings can, from the table we have to collect this information and draw a graph taking ring number on the x-axis and diameter square on the y-axis. If we can draw a line, we will get a straight line. So from this straight line, we have to find slope. Then from the slope, lambda is equal to slope divided by 4r. Then this value and this value, if both are coincide, then that experiment is correct. If there is any deviation between the experimental value and graphical value, there is some error, again you can cross check this experiment once again and you can rectify your mistake. Then this is the first application of Newton's rings. Coming to the second application of Newton's rings is refractive index of the unknown liquid we can find using the Newton's rings. In order to find refractive index of the unknown liquid, first repeat the experiment as said before. Then find diameters of the mth ring and nth ring using the traveling microscope. Then this plano-convex lens and the plane glass plate now placed in a container consisting of liquid whose value is to be determined. Again repeat the same experiment. Then find diameters of the mth ring and nth ring using the formula mu is equal to dn square minus dm square divided by dn dash minus dm dash square. Using this formula, we can find refractive index of the given liquid. In this equation, dn and dm represent diameter of the ring when air film is present, and dn dash and dm dash with the diameters of the nth ring and mth ring in the case of liquid medium. So using this formula, we can find refractive index of the unknown liquid. These are the two applications for the Newton's rings as per the syllabus. This is about theory of Newton's rings as well as application of Newton's rings. With this we can complete interference chapter completely. In the upcoming session we will go for the diffraction chapter. Then we will discuss definition of diffraction, types of diffraction, Fraunhofer diffraction due to single slit, diffraction due to double slit, remaining other concepts. Please subscribe my channel for getting regular updates. Thank you.